Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we look at the limiting sum of a GP. So let's start by looking at this geometric series here. We looked at it in a previous video. So let's look at what would happen if we add up some of its terms. So we have 2 plus 1 is 3. If we add the third term, we have 3.5. And if we add the fourth term, we have 3.75. So the sum of the first four terms is 3.75. So after I add the next term, it's 3.875. After I add the next term, which would be 1/16, I would get 3.9375, and so on. So this is the sum of the first four terms, 5 terms, and 6 terms. What is happening is because r is between -1 and 1, each subsequent term is getting closer and closer to 0. So when I'm adding them up, each time I'm adding a little less than the time before. So this is what we're going to see is a limiting sum of a GP. So let's calculate a few more partial sums. So if I wanted to calculate the sum of the first 10 terms, well, using the sum of a GP formula, it's A, the first term, times R. So R here is a half. R to the power of n minus 1 over R minus 1. So putting this on my calculator, I actually get 3.9960935. Really long decimal there. But you can see from going, fourth, fifth, and sixth partial sums, the sum of the first 6 terms was this. I really haven't added much to get to the 10th term. Let's look at what the sum would be after 20 terms. So, using this formula for S20, if I put this on my calculator, I get 3.999. There's 5 nines, and then 61853. You can see that going from the sum of the first 10 terms to the first 20 terms, I hardly added anything at all. And again, that's because each term is getting so small. What if I wanted to add yet another term? Well, let's just figure out what term 21 would be. So using the formula, Tn equals a r to the power of n minus 1, it would be 2 times a half to the power of 20. So if you put that on your calculator, you can see the term is so small, it's basically 0. It has 5 zeros and then 1, 9, and so on. So the terms are getting so small. If I add the 21st term onto the sum of the first 20 terms, it's going to make almost no difference because it's so small. So hopefully you observed that a limit has been reached. The sum started at 2, 3, 3.75, 3.875. What's happening? Each time I'm adding a term, I'm adding a little less. It is getting closer and closer to, but never actually hitting 4. In fact, if I were to keep adding infinitely many terms over and over and over again, that's what would happen. The sum would just approach 4. It would get so close to 4 we wouldn't be able to tell the difference. So we say that the sum of this infinite series here, there are infinitely many terms that goes on forever, is equal to 4. And that's why we call it the limiting sum of a GP. It's the limit of the partial sums. It is like the highest sum that the sum of these terms can go to. So, of course, a geometric series can only have a limiting sum if this happens. That is, if each term gets smaller and smaller, closer to 0. And in a previous video, we determined that that happens when r is between -1 and 1. This is the only time a limiting sum exists. Of course, if r were 2, then as we looked in the previous video, the sum would diverge. It would just get larger and larger and larger. So let's look at developing a formula for the limiting sum of a GP. So we're going to look at developing a formula for this. So here, the dots mean goes on forever. There are infinitely many terms in this series. So we're going to call it S infinity, the sum of infinitely many terms. So remember the formula for the sum of the first n terms of a GP is r to the power of n minus 1 over r minus 1. But in this case, there are infinitely many terms. So we're going to put an infinity symbol there. So what would this actually equal? Well, the thing is, we look at this r to the power of infinity. Think of this as r, the common ratio to the power of some arbitrarily large number, some really, really large number. See, if you raise 2 to some really, really large number, you will get a really large number. The same if you replace 2 with any number that's not between minus 1 and 1. You know, if I replace this with 3 or minus 4, if you raise minus 4 to the power of a really, really large number, you get a really large number. But if you raise something like a half to the power of infinity, if you raise a fraction between minus 1 and 1 to the power of a really large number, the number becomes so small it's indistinguishable from 0. So that's why we need to have this limiting sum available. Minus 1 is less than r is less than 1. If r is between minus 1 and 1, that is like it's a fraction, then that means r to the power of infinity will be 0. So what I'm really saying here is if you take a small number and raise it to a really large number, you'll get something that's very, 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 very close to 0. So substituting that in here, if r is between minus 1 and 1, this guy here will just become 0. So this becomes a times 0 minus 1 over r minus 1. So that becomes minus a over r minus 1, probably easiest if we multiply each side by minus 1. So this is the formula S infinity, the sum of infinitely many terms of a GP is a over 1 minus r. But it only works if r is between minus 1 and 1. If this is true, then the sum of all these terms will converge. As we saw in the previous slide, the sum converged to 4. But if r is outside this range, then that won't happen. The series will diverge. It'll just get larger and larger. So let's look at a few examples of actually calculating. So let's calculate each of these infinite sums. So 6 plus 2 plus 2/3 plus 2/9 plus 2 over 27, and it goes on forever. So this will have a limiting sum because the common ratio is 2 over 6 or 1/3. So S infinity, the sum of infinitely many terms, is just a over 1 minus r, 6 divided by 2/3, which is equal to 9. So if I were to keep adding terms here over and over again, their sum would get closer and closer to 9. So let's do the second one here. So this one here has a limiting sum because r, the common ratio, 3.6 over minus 18 is equal to minus 0.2 or minus 1/5. This number's between minus 1 and 1, so I can calculate the sum of infinitely many terms. It will just be a over 1 minus r. So I need 2 minuses here. So using the calculator, we get minus 15. So what will happen here? First term minus 18. Add that, you get minus 14.4. Then you get minus 15.12. And then adding that, you get a little less than minus 15. You keep adding terms over and over again. Doing that infinitely many times, the sum will approach minus 15. So let's try this question, which is a little harder. So we're told the sequence 1 plus x squared plus x cubed and so on has a limiting sum of 1.5. What is the value of x? Well, this is clearly a GP. A is equal to 1 and r is equal to whatever x is. So to find the value of x, let's just substitute this into the limiting sum formula. So s infinity, so that will be a over 1 minus r. Now, I was told that the limiting sum here is 1.5, so I can just rub this out. I get 1.5 is equal to 1 over 1 minus x. So what I'm going to do is multiply each side by 1 minus x. And then I'm going to divide each side by 1.5. So 1 divided by 1.5 is equal to 2/3. So now, all I need to do is say, what do I minus from 1 to get 2/3? Well, x is clearly 1/3. 1 minus 1/3 is equal to 2/3. So that is the answer. This is actually the sequence 1 plus 1/3 plus 1/9 plus 1 over 27 and so on. If I keep adding terms and add infinitely many terms, this sum here will get to 1.5. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.